Good day from Chem Help ASAP. This video reviews some of the reactions that demonstrate the idea of stereochemistry in a standard 2-semester sequence of Organic Chemistry 1 and Organic Chemistry 2. The list of reactions covered in this video is not comprehensive, but the most common examples should be included. Note that this video is intended as a review, and I'm assuming that you already understand the basics of stereochemistry, including assigning stereochemical configurations. Let's revisit some terminology. So stereochemistry refers to the spatial arrangement of atoms within a molecule. Stereochemistry is closely associated with chirality or handedness of a molecule. The most common examples of stereochemistry in organic chemistry involve tetrahedral carbons with 4 different substituents. So these carbons are often drawn with hashed and wedged bonds to show the spatial arrangement of atoms about the central carbon. It is very easy just to look at a molecule and search for carbons with dashes or wedges to find stereocenters. I confess I do this all the time. The topic of stereochemistry, however, is not limited to tetrahedral carbons. We'll see one example in this video in which we'll discuss stereochemistry without a tetrahedral carbon. There are many different types of stereoisomers, but most university-level organic classes focus on just 2, enantiomers and diastereomers. The textbook definition for an enantiomer is a non-superimposable mirror image. I am not a fan of the term non-superimposable. I think it's a bit intimidating. Non-superimposable is just a fancy way to say that you are comparing 2 structures that are not identical. So to be enantiomers, 2 molecules need to be not identical and mirror images. The other type of stereoisomeric relationship we'll mention is the diastereomers. To be diastereomers, 2 molecules need to be not identical and non-mirror images. To be clear, they need to be stereoisomers, same connectivity, but only different in terms of spatial arrangement of the atoms. If the stereochemistry in your molecule arises from tetrahedral atoms, then you can take a shortcut here. To be enantiomers, all the stereocenters in the molecule must be inverted between the structures. To be diastereomers, you need to have at least one stereocenter inverted, but not all the stereocenters. If you invert all, then the 2 molecules will be enantiomers. Okay, enough terminology. Let's see some use cases for stereochemistry. Perhaps the first brush with stereochemistry for students is with cyclohexanes. With cyclohexanes, specifically di-substituted cyclohexanes, you can talk about the relative orientation of groups around the ring. If both groups are on opposite sides of the rings, then the groups are trans. If they are on the same side, either both up or both down, then the groups are cis. The relationship of these 2 isomers, trans and cis, is diastereomers. When we show these compounds as chair structures, the stereochemistry and relative orientations of these groups are preserved, although they might be harder to recognize. In the top chairs for the trans isomer, note that the Br and Cl are always trans. One is up and the other is down. Axial up, equatorial down, and equatorial up, axial down. For the chairs of the cis isomer, both the Br and Cl are always cis. In this case, both axial up or both equatorial up. So these are diastereomers, although you may not have known the term when you first encountered cyclohexanes. Almost certainly, by the time students encounter the SN2 reaction, they would have been briefed on stereochemistry. And understanding the SN2 requires one to already understand stereochemistry. So the SN2 reaction involves inversion of stereochemistry. Here is an SN2 reaction. The bromine is the leaving group on the top face of the molecule. Attack by the azide occurs from the opposite face in one step, no intermediate, so the azide is down in the product. The stereochemical configuration does change from S to R, but do not assume that the configuration will change. It depends on the structure of the molecule and the nucleophile. R and S are nomenclature labels and do not always correlate with structural changes. The lower reaction emphasizes the idea that the change in stereochemistry only occurs at the reaction center. The left stereocenter is not part of the reaction, so it remains unchanged. Sometimes students mistakenly invert all the stereocenters in a structure, but only the reaction center is affected. How about the SN1? The SN1 is different from the SN2 because the SN1 goes through a carbocation intermediate. In the reaction on the screen, the leaving group is again the bromine. The reaction is a solvolysis. The bromine leaves and the carbocation forms. At that point, the stereochemistry of the original stereocenter is lost. That formerly tetrahedral carbon is now flat, and the nucleophile, methanol, can attack freely from either the top or bottom face. That's exactly what happens. Two products are formed, one with the methoxy down. This is called the retention product, and the other with the methoxy up, the inversion product. People often call this scrambling of a stereocenter. The other stereocenter is not part of the reaction, so it is unchanged. The product mixture consists of two diastereomers, two stereocenters with one changed but not both. The E2 has stereochemistry. This might be a surprise because the elimination generates an alkene, and alkene carbons are not tetrahedral. It seems that eliminations get rid of stereochemistry. That is true in a sense, but alkenes can have their own spatial arrangement. Alkenes are one of the exceptions I referred to in an earlier slide. You do not always need a tetrahedral carbon to discuss stereochemistry. So on the slide is an E2 elimination, and there are two possible alkene products, the E-alkene and Z-alkene. These are diastereomers. Non-superimposable, non-identical, and non-mirror images. That's fine, but which product, E or Z alkene, will we get from this reaction? We need to look at some Newman projections to answer that question. Here are the three possible staggered Newman projections for the starting material. These Newman projections are looking down the C2, C3 bond of the starting material. Remember that the E2 favors having the leaving group and beta hydrogen anti in the reactive conformation. The first Newman projection has an anti-beta hydrogen to the leaving group, although we do have an unfavorable gauche interaction here. In the second Newman projection, we do not have a anti-beta hydrogen, so we can ignore this one. It will not lead to an E2 product. The last Newman projection does have an anti-beta hydrogen, but now we have two unfavorable gauche interactions. So between these two projections, the left is more stable, it will be more prevalent for the reaction, and will lead to the major product. In this conformation, the two methyl groups are on opposite sides of the structure. So the major alkene will have methyl groups on opposite sides of the alkene, the E-alkene. The other conformation would lead to the Z-alkene. So even though eliminations do not form tetrahedral centers, the alkene is a potential site for stereochemistry. E1 reactions are similar, but because of the carbocation intermediate, they tend to favor the more stable alkene geometry. Stereochemistry is also very relevant for additions to alkenes. So when adding something, let's just say AB, to an alkene, the addition can give the A and B on opposite sides of the alkene, the trans product from an anti-addition. If A and B are on the same side, then you get the cis product by way of a syn addition. The cis and trans products are diastereomers of each other. Some reactions do not form just one or the other. You can get either, which is to say a mixture of both the cis and trans products. Let's see a few examples. One common example of a syn addition is the catalytic hydrogenation. Both added hydrogens are on the same face, the cis product. The hydroboration oxidation is a two-step process. The initial hydroboration is the syn addition, and the OH replaces the carbon-boron bond in the second step with no change in the stereochemical configuration. So both the added H and OH end up on the same face of the structure, a syn addition. The classic example of an anti-addition is a dihalogenation. The reaction goes through a halonium ion. I'll draw it quickly in the upper left. In this case, it's a bromonium ion. The second halogen comes in through opening of the bromonium ion from the opposite face to give the trans product. Epoxidation followed by ring opening also gives a net anti-addition. Just like in the bromination, the three-membered ring of the epoxide, drawn in the upper right, is open from the opposite face to give the trans product. Not all additions are strictly syn or anti-additions. Reactions that tend to give mixtures of both cis and trans products often involve strong acids and go through a carbocation intermediate. In this hydrobromination, the alkene is protonated to give a carbocation. Let's assume the proton came in from the top face to give this carbocation. The carbocation can then be attacked from the top or bottom face to give either the cis or trans product. Hydration reactions with acid and water also tend to give a mixture. Now we are at the Diels-Alder cycloaddition. The Diels-Alder has stereochemistry all over it because you form several new tetrahedral centers. Let's start by looking at the diene. When the dienophile adds, this is an addition after all, to the diene, the orientation of the groups on the end of the diene are predictable. The A and D groups will be cis with respect to each other in the new ring. The B and C groups will also be cis. Let's now focus on the dienophile. Groups that start cis on the dienophile, like the E and G, finish the cycloaddition cis in the product. So the Diels-Alder is a syn addition across the board. Let's now focus on the idea of endo and exo. Here are our fully substituted diene and dienophile. If these react, we can get two possible products that are consistent with what we discussed on the previous slide. Note that these very similar looking products differ in the relative orientations of A and F. On the left, A and F are cis. On the right, A and F are trans. These are diastereomers. There are 4 stereocenters. 2 are different, and 2 are the same between the 2 compounds. This is the difference we see in endo and exo products, which are diastereomers of each other. At the bottom is a proper Diels-Alder. There are 2 new stereocenters. Let's number these carbons in the diene and dienophile. And now the endo product. Note that one new stereocenter came from the diene and the other stereocenter came from the dienophile. One diastereomer is called the endo product and the other is exo. There is a tag to a video in the upper right for how to identify which is endo and which is exo, as well as predict whether the endo or exo product will form in a reaction. If you have studied the chemistry of sugars, then you have likely been exposed to anomeric centers. When sugars exist in their cyclized forms, a new stereocenter forms at C1 of the sugar. Both of these sugars on the screen are glucose with identical stereochemistry at all carbons except at the anomeric carbon, C1. These structures are called anomers, and they are more generally examples of diastereomers. Sugars that differ at their anomeric center are distinguished as either alpha or beta anomers. If the anomeric OH is cis to the CH2OH group, then it is the beta anomer. If the OH and CH2OH are trans, then it is the alpha anomer. Those are some highlights, but stereochemistry is relevant to any reaction that forms a new stereocenter. Two additional examples are on the slide. On the top, reduction of a ketone forms a new stereocenter. In these products, the new alcohol may be cis or trans to the methyl on the other side of the ring. So we could possibly observe two different diastereomers from this reaction. In the lower reaction, starting with the same ketone, we could make an enolate and methylate it. The two methyl groups could be cis or trans relative to the methyl that was already on the ring. Predicting these outcomes is beyond what I teach at the college level, but both of these reactions and their diastereoselectivity have been well studied in the chemical literature. That was a quick review of stereochemistry. Please leave a comment, leave a like, or subscribe to the channel. Questions, of course, are also always welcome. Take care.